start recording. All right, so OBS is up and running. So we are now moving on to the next module in Canvas, which is titled Von Neumann Architecture and Memory. And this is the module that contains the description of an SR latch. It is already in there, but today's focus is going to be how do we track changes in a circuit. All right, so I think by this time my router is up and running. Very good. So I will go ahead and use my tablet to show you guys the SR latch circuit. And then we are going to go track down what happens when we make changes to the circuit and follow these instructions that are currently being projected in order to track those changes because that's also what you need to do in today's lab. Um, so it would be a good idea to try to really understand all the concepts because for people who do not get a good understanding of the concepts, today's lab can be excruciating, frustrating. So we'll hopefully you won't experience that. Okay, so hopefully you will feel that, oh, okay, I really understand what is going on and everything is good. All right. So let me switch to the tablet first because I do want to show you. Oh, I have to turn on the screen share function. Yep, it's on. And then refresh this again. Oh, I have to put my computer on that network too. So there we go. All right. Yeah. All right. So the SR latch circuit looks like this. Okay. It has got two input pins. One is called S, one is called R. It has two output pins. One is called Q, which is the quote unquote unnegated output, and then one is called NQ, which is the negated output pin. Okay, so all of these are actually in the notes as well. Okay, so if you refer to the reading material, the circuit is actually described, but not as a circuit. Okay, it is described in text. So we'll kind of talk about that when we have time. But the current focus is really just, okay, what kind of a circuit is it? So this is kind of the circuit. The output of the NAND gates go to the two output pins, Q and NQ. S and R would go to one of the two inputs of each respective gate. So we're going to name the gates. This is named N1. This is named N2. The output of N1 is actually going back and serve as the input to the other input of N2. And then the output of N2 in return is going back to serve as the second input of N1. Okay, so this is the SR latch. Okay, so I'm just going to put a title here. This is called the SR latch. It is a very simple circuit because the NAND gate is one of the simplest gate that we can make using only two P-type transistors and two N-type transistors. That was the first thing that we did in this entire semester. So this circuit here that we are seeing only needs 8 transistors. 4 N-type transistors, 4 P-type transistors. So it's a pretty simple circuit by any means. And yet it is kind of interesting because it is actually quote unquote the most elemental form of computer or binary computer memory. So do we have any questions about the circuit itself? No questions about the circuit itself? All right. So what we'll do is we'll try to kind of track down, okay, changes. And that is the whole idea of this particular module. So we're going to go back to the module, okay, the reading material, and kind of understand, okay, what are we talking about here? The terms, okay, a port is a point of connection on a component, such as a gate, and that point of connection connects to what we see as a wire in Logic Sim. So now, switching back to this diagram, what are the ports? So we have a port over here, we have a port over here, we also have a port over here for the NAND gate. For a input pin, the only port is here. For an output pin, the only port is here. In other words, because we have been using Logisim for a long time, right? So anytime the wire actually snaps to a component and make an actual connection, that is what a port is. Okay, so a port is really just a name referring to a connection point on a specific component in Logisim. Are we good with that term? Yes. So are you referring to the crossover like here? You mean here? So that is not a port because it is really just a wire that has multiple components. Okay, so that is not considered a port for the purposes of this discussion. So that's a port, but what you mentioned is related to what a node is. So we'll go to talk about what a node is right next to it. So a node is a collection of wires that are electrically connected. In other words, logically speaking, they are the same thing. So now let's go back to the circuit and identify, what a node is. So we'll switch back and forth a little bit here. So a node in this case, okay, there are some simple nodes and then there are some kind of like more involved nodes here. So I'm going to switch to a marker pen. Hopefully it will work the way that I think it will work. So this itself is a node. Okay, that's a little bit too thick, but I think you guys get the idea. So I'm going to go back here. But another node is a little bit more complex. So this wire combined with this wire is also a node. Now, this particular node connects not only two ports together, it actually connects three ports. It connects the output port of N1 to the input port of Q, but also to the first input port of N2. So are we doing okay so far? The thick line that you're seeing here is a single node. It makes the logical connection between three individual ports. Are we good? So we got ports, we got nodes. Nodes are essentially electrical connections between ports. Are we good? All right. So I'm going to go back because the thick lines are really kind of thick, but I think it made the point of to explain what a node is. So these terms are from electrical engineering. A component is typically a gate or device that has input ports and output ports, sometimes both, sometimes only one. So in our particular example, this is a component, okay? It is an input pin. It only has one output port. This is another component. It is a NAND gate. It has two input ports and one single output port. And this is an output pin, which only has one single input port. So now we have all those individual concepts. So the next one is the propagational delay, which we talked about a little bit in the previous class, other than the practice exam on Tuesday. So a propagational delay is it takes a short amount of time. This is the amount of time for a component to update its output port or ports, depending on what component we are talking about, after at least one of the input ports is changed. This amount of time is called the propagational delay. Do we have any questions about what that is? Now, if this is the first time you read the sentence, it might take a little bit longer to absorb, but if you have been reading the material, or, I think we mentioned this actually in the previous class too. So if you have been taking notes, reading the material, I think it's fairly obvious what it is. But do we have any questions about the propagational delay? How it is defined in the context of ports, nodes, and components? The bottom line is the propagational delay has nothing to do with a node. Okay, it is only the amount of time that it takes between the change of the input of a component to the change of to the corresponding change of the output port of the same component. Yes. That is correct. Yep. So the input pin has no propagational delay whatsoever because it only has a single output port. And then the output pin also has no propagational delay to speak of because it only has an input pin. Yep. All right. Yep, that is correct. Okay, good observation. All right. So in pseudocode, the logic can be summarized as follows. We usually start with a starting state, and it is signified with NC, which stands for node connectivity. So the initial changes to the input pins are in boldface on this row. For the initial NC or node connectivity row, update the ports that are connected by nodes to the ports of the updated input pins. Okay, so we'll talk about this. Okay, so we are actually going to use these instructions in today's class, and I'll go through one simulation of the mechanism of the SR latch. Okay, so as we go through that, you can either take notes or just kind of focus on what I do and relate what I do back to the reading material. All right, so the next step, okay, so this is how we start the whole thing. And then the next step is perform the following steps until there is no change from the last step. In other words, this is a while loop. It is basically saying, okay, keep doing this until there are no changes from the last step, which also means this is a do while loop because we have to go through at least one iteration. Does that make sense? Okay, because you cannot get to the PD row until you're done with the first two steps at least once. So we start with the NC row, okay, or node connectivity, which can be the initial one. Depending on the wiring of the circuit, update all other ports of the same node connected to a port that is just changed. In other words, the node connectivity is basically saying, okay, the output port of this component just updated or it got updated for whatever reason. Then all the other input ports that are connected to this same node, they also have to update because guess what? There's a copper wire or bunch of copper wires connecting the output port that was just changed to all of these other input ports. So the update of the input ports because of the change of the output port and also because of the node connectivity will be updated in this particular step. And then the next step is called the PD or propagational delay. So after a propagational delay, analyze and compute the output ports of every component that has at least one of the input ports changed because of the previous NC step. In other words, the NC step would update the input ports of components. And then all the components that have at least one of their input ports changed can potentially have the output port changed as a result after a propagational delay. So the PD step is for figuring out, do we have a change of the output ports of these components? And if so, what it is? What is it? Are we understanding, kind of in abstract terms, what these things are specifying? It can be a little bit difficult to absorb right now, but by the time we go through a few simulation, I think it will be a lot more clear as to what each step is trying to explain. So keep this in mind, okay? You can pull up the computer on your workstation and kind of read this on your own. When I have to switch back and forth, you can stay on this one on your own device, okay? On your own computer, laptop, cell phone, whatever, right? Because it is probably helpful to refer back to this description as you make a connection between my demonstration and the instructions that I'm actually demonstrating. All right, so now we move on. Okay, so for the rest, I'm just going to run this through here. So at this point, I need to make a table. Okay, and I'm terrible with drawing straight lines and making tables. So we'll give it a try. But I'm not sure how well, I can do this, and let me see if I can make layers, okay, which is, nope, that's not layer. Let me see if I can make additional layers. I don't think that is possible with this tool. Hmm, okay, doesn't look like I can make additional layers. Hmm, no, I don't think any one of these is, what is this? Nope. Okay, well, I can still make it work. It's just that, if I have access to a feature called layer, then I can just keep this, on the bottom layer, and then I can make additional stuff on top of it. So that would be handy and nice to have, but I do not seem to have access to that. Okay, but that's okay. All right, so in the table, I would have columns. Um, you know, the first column is going to be, what kind of cycle it is. Okay, so I'll just say, what kind of cycle. And then the next column, or the rest of the columns, would be corresponding to the ports. I have a component called S, I have a component called R. Both of those are pretty easy, okay, because they are just input pins. So each one only has an output port. Okay, so this is how I would do it. So the name of the component is on top, and then the name of the ports is below the component. And at least that's how I'm doing it with the tablet. And then we have N1. Okay, so N1 is a little bit special because it has input 0, which is the top. It has input 1, which is the bottom of the input pin, and or port, excuse me, and it has output. So what this means is in 0 is corresponding to this input port. In 1 is referring to the second input port. Out is referring to the only output port of N1 as a NAND gate. And then N2 is kind of the same thing. It has got in 0, in 1, and then also just an output port. And then we have Q and NQ. Those two are super duper easy because Q as an output pin has an input port. Now, it sounds kind of opposite to what they are, but that's exactly the way it should be specified, is any output pin has an input port because the quote unquote output nature of an output pin is to circuits that are outside of the circuit that we're looking at. Is that okay? It's kind of like, when you specify, okay, the input pins are like parameters to a function. Somebody has to specify those values, right? But inside the circuit, they supply the values to be processed. And that's why they're called input pins. But their values are specified by somebody else, okay? But to the inside of the circuit, they serve as outputs because they just have to say, oh, okay, somebody specify S to be a 0 and R to be a 1. So to the rest of the internal circuit here, R and S serve as quote unquote outputs. But to the output pins, Q and NQ, they are like return statements in C++. Okay, so when you say return and then an expression, that expression is actually of a output nature in a way, but you have to be able to compute it. So the circuit itself is responsible to come up with the value that we are returning. The pins, the output pins, the port to the output pin is serving as quote unquote an input to the pin itself. Okay, so the in and out is with respect to the component itself, not with respect to what this particular circuit is connected to. So it's a perspective kind of thing. Are we good with those concepts? Okay, all right. So initially, we say, well, we don't know anything about the entire circuit. Okay, so we just fill everything in with question marks. Okay, we simply do not know. And then the first thing we'll do, okay, we'll do an NC here, is okay, so assuming both of the S and the R pins are going to be zeros, in other words, somebody from outside the circuit decides, let's go ahead and turn the input pins S and R both to zeros. This is from outside. So according to the instruction, for the initial NC, these two zeros would be in boldface. So I'm just going to emulate boldface by writing over it again. Okay, so they're in boldface. So the NC is going to look at these two. Now, in this case, because we have the circuit diagram up, so I can just use the circuit diagram to say, oh, okay, where are they connected to in terms of node connectivity? In other words, what input pins are going to be updated because S and R changed their states from whatever it used to be, which is unknown, to zeros. So who else is going to be impacted or changed due to node connectivity? Can somebody tell me? Yes. Mm-hmm. And they're specific because S is connected to by this node, this wire, to in zero of N1. So N1 in zero is going to get a zero. Okay. So but this zero is because of the input pin S. The R input pin connects to the second input pin of N2. So we look under N2, we look at the second input pin. So that also becomes a zero. So are we clear on how we update on an NC row? It is because of the wiring, because of node connectivity. Is that okay? So now, after an NC that is, that actually spreads some, changes, you do not have a choice but to go to a PD. Okay? So the PD is going to say, okay, in the previous row, which is guaranteed to be an NC row, is the input of any component changed? So if nothing is changed, then the PD row can be empty. Okay, it's basically saying nothing is changed. Okay, we're all good. But in this case, we can see that N1 or at least one input of N1 is changed from unknown to a zero, right? So that is one change of at least one input pin of a component. The same thing for N2, because N2 also has its second input pin or second input port changed. So that is also a change of at least one of the input ports of a component. So as a result, the PD row has to figure out, all right, well, is the output of any one of these components now determined? Okay, so now what do we do? Okay, so if you're thinking we need both inputs to decide the output of a component, then you need to go to the truth table. Okay, so you need to go to the truth table of the NAND gate, and then you look at what the configuration that we have now, and then you say, can we actually know the output of N1 and also the output of N2 now that we know that one input of N1 is guaranteed a zero, the other input we don't know, and then one input of N2 is also guaranteed a zero, even though the other one we do not know. So the question is, how can we determine that? All right. Yep. It is a NAND gate. NAND means what does the end of NAND represent? It is a NAND gate. We know that from diagram because of this little bubble, which is basically acting as a negation. So it is a negated AND gate. So when you refer back, but your logic is correct, okay? The way you think is correct. It is just that it is opposite, okay? So that means, oh, we actually can determine that the output of both N1 and N2 would be ones. So there's a one here, and there's also a one here. Are we good so far? So on this row, on the PD row, we do not say, oh, Q is going to be a 1 and NQ is going to be a 1, because the PD row is only responsible to indicate a change of the output port of a component where the previous NC row has a change of the input port. Yep, that is correct. So the NC row is changing things due to the wires. And then the PD row is changing things or output ports because of the components. Yep. hmm All right, so that's the end of the PD row. Okay, we are not changing Q or NQ at this point. That would be the responsibility of the next NC row. So the next NC row says, okay, um, were there any output pins changed because of the previous PD row? We look at the PD row and we go like, yep, this change is on an output port, this change is also on an output port. So now the N0 has got something to do because now it has to go like, okay, where is the output port of N1 connected to? So you look at the wiring, okay, it goes here, but it also goes here. So as a result, this one that we are seeing from the previous N0 is going to also be reflected. Okay, I need to align things on the tablet. It also goes here, but it also goes to Q. So both of these ones, okay, so both of these two ones are corresponding to this one over here. But we have to do the same thing about this one here, or the output port of N2 being changed to 1 also causes some updates because of the wiring. So in that case, it is making changes. You can follow the wiring on the diagram, right? So you can look at this output here and go like, okay, who is affected by the change to the output port of N2? That would be NQ. Okay, so we put a 1 on the NQ here. And it is also, if you look at this wire, it is also going to the second input port of N1. So that means we also have to update this one right here to a 1. Is that okay? Well, since we got the NC row being non-empty, so now we have to go back to a PD row and try to figure out what is going to happen here. So we go back to a PD row. So the PD row is asking, um, which component has at least one of its input ports changed? So you go like, well, the Q and the NQ got something changed, but since the Q and NQ do not have an output port, so having the input port change means there's well nothing that we have to process with a PD row. Okay, so the only two components where they have both input ports and output ports would be N1 and N2. So you look at N1, okay, this is changed to a 1. So now we try to determine the output. So the output is going to be, oh, it's still going to be a 1, but we do not write a 1 here. Okay, so let me put my cursor at the place where we do not write a 1. Okay, so right here, we do not put a 1 here because it is not a change. Okay, if it was a 1 to begin with, and it continues to be a 1, even though one of the input ports have changed, we do not write anything here. All right. Same thing goes for this output port here, because at this point we know that N2 has one input being a 1, the other input being a 0, but the output continues to be a 1, which we knew already, so that one continues to be here, but we do not write anything here, because when you write something in this table, it is indicating a change from a state where from before. And we are not seeing a change of the output port of N1 or N2. So when you have a PD row that is completely empty, then we have reached what we call a steady state, and you can stop that particular phase. In other words, just changing S and R from whatever they were to both zeros, now we have come to a steady state, and the output of the circuit will be outputting 1, 1. Are we good so far with this simulation at this point? So we good? Okay, no questions. All right. So now we go like, what if I am to change, um, so when I do this, I might run out of space. Okay, so I have to be a little bit careful of, how to continue with this trace here. But we're going to say, okay, what if, let me see, I need a way to capture this and then move on to the next one. So this is what I'll do. Okay. So if you want to copy this, go ahead and copy this. But I'm going to make some changes so that I re-record the current state and then move and then erase a part of the trace at this point. So are we ready for me to erase a part of this? Okay. All right. So what I'm going to do is something like this. Okay. So I am going to first erase all the question marks. So instead of all the question marks, I just write down what we already know about each one of those, columns. So I'm just copying from 0, 0, 0. This is now a 1. This is now a 1. This is now a 1. That is still a 0. This is a 1. This is a 1. This is a 1. In other words, I'm just recapturing all the state of all the ports up to this point. All right. In your lab, you do not need to do that, okay? Because you're given a table that is much longer than this one, so you won't run into this problem, okay? I have to do it simply because I only got so much space, to kind of continue for the next step. All right, so now that I have copied everything, now I can go ahead and erase, the rest of the rows so that I can start from scratch. So the next time, or in the next cycle, okay, in this class, I'm gonna say I will change both, S and R to ones at the same time. And because I mentioned that, any changes to the input pins will be boldface, so this is how I kind of simulate the effect of a boldface. So they're both ones, but because this is a change triggered by the circuit external to this particular circuit here, and that's why they're bold-faced. So because this is an NC row, that means I'm gonna have to track down the wires and find out, hey, if S is changed from 0 to 1, who else is gonna change from 0 to 1? Well, according to this, in 0 of N1 is going to change from 0 to 1 also, as a result of S being changed. Okay, so that's fine. We'll do that here. And then at the same time, if you look at R, it goes to the second input of N2. So that means N2 in bracket 1 is also going to change from a 0 to a 1. All right, so we're going to change that. Okay, and that's the extent of this entire NC row because the input pins only has a single wire going to one of the input ports of the NAND gates. Same thing with the R going to N2. So we have now concluded the NC row, as a result of the input pins S and R being changed simultaneously from 0 to 1. Are we good so far? Any questions? No questions? All right. So now we go like, okay, let's see if any component has the input pins changed. So we look at N1 and N2, which are the only two components that have both input and output pins. So we will go like, oh, well, for sure, N1 has one of its input pins changed. So now we have to recompute or figure out whether the output is going to change from a 1 to something else or not. So now we have a PD row. Okay, so here's a PD row. So on this PD row, we can say, hey, with N1, now both inputs are ones. This one was coming from before. This one was coming from the NC row. Okay, so now your N1 has both inputs being ones, and the output is going to be a 0 because it's a NAND gate. All right, so we put a 0 here. And this is a good time to kind of mention if anyone is trying to figure out how do we know the output of N1 is a 0 when both inputs are 1s, it's the truth table of a NAND gate. Okay, that is something that we talked about day 1 of this entire class. Okay, so your next exam does not have this. Okay, in other words, the exam on next Tuesday does not have this in the scope, but the exam after that does. Okay, so I want to kind of just point out what is important for you to maybe jot down in your notes. Okay, but it's also the same scenario for N2 because if you look at N2, this one is from before. This one is from the NC row itself. It's due to R being changed from a 0 to a 1. But the effect is both inputs of N2 are now 1s, which means the output is also going to change to a 0. Are we good so far? Okay. So now we are done with this PD row. Okay. But the NC row, we now have to follow up with definitely another NC row. Anytime a PD row is non-empty, you have to follow it up with an NC row because the change of the output of N1 is going to trigger some other ports to change. the change of the output of N2 is going to cause the output or the input port of some other things to change. So now with the NC row, we have to just kind of follow the trace here, right? So we just look at the output of N1, which is becoming 0 at this point, and we go like, where is it going? Well, it's going to Q, okay? So Q is also going to change to a 0, but on the NC row, but at the same time, okay, there's a little tap here, but it's essentially logically the same node. So it also goes to the first input of N2. So now we go like, okay, that's kind of interesting because now this is also changed to a 0. And then we look at the output of N2, it goes to NQ, and the output of N2 just changed from a 1 to a 0. So this 0 will now be, quote unquote, spreaded to NQ. So NQ is now going to be a 0. And at the same time, there's a little tap here. That tap goes to the second input of N1. So that means N in 1 of N1 is also going to change to a 0 because of node connectivity. So I'm just going to pause here to make sure that we all understand why on the third row, which is an NC row, we have a bunch of zeros in that particular way. Do we have any questions about the trace up to this point? Yep, that's just the nature of this particular trace. So that is not a general pattern when we track down the changes. Uh-huh. No, they do not have to be the same. They turn out to be all the same only because this output changed from a 1 to a 0. This output also changed from a 1 to a 0. That is the only reason why we see all zeros on the NC row that follows it. In other words, in a different circuit, okay, or in a different configuration of the same circuit, it is possible that one output pin goes from a 0 to a 1, and at the same time, the other one goes the opposite way from a 1 to a 0. Then whatever this thing goes, or whatever this state is, will be copied here and also here. Whatever this turns out to be will go to here and also here. Yeah. So the fact that they're all zeros, is coincidental for this particular example. Are we good so far? Okay. So if you guys want to, I can also kind of make some relatively thin lines, like really, really thin lines, or a slightly different color. Okay, so let's look for a gray color here. Then I can go explain, this 0 is linked to this being a 0. It is also linked to this one being a 0. And then this 0 in return explains why this is a 0, but it also explains why this is a 0. So, now in your trace today for the lab, you do not have to draw those gray lines, okay? Because, I'm just doing this so that we can kind of visualize, which 0 is responsible for which other zeros. But it's important to understand the concept of NC is just saying, okay, some output changed because of propagational delay. That output port connects by some wiring to the input port of something else. And as a result of the wiring, those input ports would change at the same time because it's just because of the conductor connecting the output port to the input ports. That's the whole purpose of the NC row. The PD row, on the other hand, depends on the behavior of the device or of the component. If you have an AND gate, it behaves differently compared to an AND gate. If you have an exclusive OR gate, it behaves differently compared to both the AND gate and the NAND gate. Okay, so PD row depends a lot, mostly solely on the components. NC row is just because of how the wires are drawn. We good? All right, so let's continue with this trace here. So the next one is always going to be a PD row. In other words, we always alternate between PD and NC. And let me change the color back to just the regular color. Okay, there we go. All right, so what this PD row has to do is to look at the components where at least one of the input ports have changed. So if you are saying, if you're noticing, tech, you seem to be using that phrase a lot. Like this is the fifth time you use that phrase. Well, congratulations. You are starting to make a connection between what I'm doing and what I'm saying here with the instructions that we started off with. Okay. So now we look at all the components. Okay. SNR are not really issues. They don't have an input pin to begin with or input port to begin with. So we are not concerned about SNR. But N1 has input ports and it has a single output port. So now we have to go like, okay, did we change one of the input ports of N1 in the previous NC row? Yes, we did. So now you have to go like, well, is that going to change the output of N1? Yes, it was a 0, right? And now we have one of its input port being a 0. So the output is going to change from a 0 to a 1. Okay, so let me write it down first, and then if there are questions about that, I can try to answer that question. But there's a 1 here. Do we have any questions about why the output of N1 is changed from a 0 to a 1 in response to one of its two input pins being changed? No questions? This 0, which is due to this 0 here, this 0 in return changed the output of N1 because N1 is a NAND gate. If at least one input of a NAND gate is a 0, the output is going to be a 1. It used to have both inputs being 1s. Now one of the input is a 0, and as a result, the output now becomes a 1. But that is also a change because it had an output of 0. This is a change, so we have to write it down. Okay? But you can probably say, oh, but this circuit is vertically symmetric. In other words, if I were to draw a line here and pretend that line is a mirror, then the top half and the bottom half look exactly the same, right? And because the way we configure the pins S and R are also symmetric because they're both zeros and now they're both ones. So that means, oh, okay, so we kind of know what is going to happen to the other NAND gate because the other NAND gate, which is N2, also has its input 0 experiencing a change from a 1 to a 0, which means from the perspective of N2 as a NAND gate, now it has in the inputs of 0, 1, so the output is going to change to a 1, 2. And because it was a 0, we have to write it down as a 1 because it is a change. Are we good so far? Okay. So now, for those of you who are keen at noticing patterns, you would notice that tech, aren't we getting back to the first NC row now? Because now, S and R are both ones because those are input pins. So nothing you do inside the circuit will ever change S and R because that has to be initiated from the outside. Okay, so S and R are guaranteed to be the same regardless. Okay, but when you look at N1, um, after the NC, of it changed from a 0 to a 1 because it's node connected. Um, in 1 was a 0 before, what was a 1 before, but now it is changed to a. Okay, so I think, let me see. I'm trying to detect whether we can now determine this is a loop already, and the answer is no. We need one more step to see that this is a loop. Okay, so we'll go for one more step, which is another NC row, because you always alternate between PD and NC rows. Okay, so we go for another NC row. So the next NC row is going to look at the output change from the previous PD row, which in this case is, oh, this output is changed. Let's look up the wiring and find out where it connects to. Well, this is the output of N1. it connects to the in port of Q. It also connects to the first in port of N2. So we're going to make those changes on this row of this NC row. Okay, so we're going to say, this is going to change to a 1, okay, right here. And then this is also going to change to a 1 as a result of this output being a 1. Are we good so far? Okay, so this is pretty much a repetition of what we have done already, but but it's just a different polarity. And don't forget the other output pin that also was changed, which is this output of N2, which is corresponding to this port in the circuit diagram. So now we have to track it down and go like, okay, which other input ports are you connected to? So we track this down. It goes to NQ. NQ is now changed to a 1. And then we track down the tab over here, and it goes to the second input of N1, which is in 1 of N1. So now that is also now changed to a 1. Are we good so far? But if you look at the state of all the input ports and all the output ports, we are now back to the first NC. In other words, on the first NC, S, R are both ones. Those have never changed. N1, because of how it connects to S, would also remain 1 all the way throughout. In 1 was a 1 before. It got changed to a 0, but now it's back to a 1. Out of N1 was a 1. It got changed to a 0. Now it's back to a 1. In 0 of N2, kind of the same thing. It was a 1. It got changed to a 0 at some point, but now it's back to a 1. In 1 of N2, same deal. It started off with a 0. It got changed to a 1, and it is still continue to be a 1. And this one has to do with R being a 1, and because those two are connected by a wire, R cannot change, and neither can in 1 of N2 change ever in this particular trace. What about the out of N2? It was a 1, changed to a 0, now it's back to a 1. Q, same thing. Q and NQ are not really too big of a deal because whatever the output of N1 and N2 are will go to Q and NQ respectively. So we're not too concerned about Q and NQ. They're just some output pins. But anyway, what we can see now is on this particular NC row, if you take into consideration of all the things that have remained unchanged from the previous row, we are now back to the first NC, which means any further simulation is pointless because we're just repeating that loop. Because now we're in the very same condition as the first NC. So if I were to label, okay, let me go ahead and label the NCs. This is NC1, this is NC2, this is NC3. NC3 is exactly the same as NC1, which means if I look at the PD, if I have a PD right after NC3, it would look exactly the same as the PD right after NC1. This becomes a loop. It will never end. We are not going to get to a steady state in this particular configuration. Are we good so far? All right. So that means the current configuration of this SR latch does not end up with a steady state. Instead, it is an oscillator. It will keep oscillating. The output Q and NQ would just go from 1 to 0, back to 1, back to 0, back to 1, back to 0, and then 1, 0, 1, and so on. Are we good so far? This is not how we use an SR latch properly, by the way. Okay? So the reason why I use this particular trace instead of a useful one is because the useful one is your lab. And I just don't want to do your lab for you. So, but the idea of what to do with an NC row and what to do with a PD row is completely illustrated. Are we good so far? Yep, go ahead. Mm-hmm. Yep, yep. And as a result, it will not have a steady state. Yep. All right. So at this point, I'm going to switch to the next slide when you guys are ready. So if you're taking notes, let me know. If nobody else is taking notes, I will switch to the next slide, which is going to be an interesting truth table. So are we good so far? Okay, I'm just looking at the time. And one thing you can also do is to double check, make sure I'm still recording. Okay, one. Two, look at the clock because I typically start recording at really close to 9 a.m., if not exactly at 9 a.m. So that will give you an idea of how far do I have to get into the recording to get to a particular screen. If you find a particular screen to be useful, go to the video, go to that screen, pause the video, take a you know just kind of grab that portion of the screen, slap it onto your own document. It can be Google Doc, can be whatever you want to use, and then you have that already captured. Then you can start to annotate it. Okay, I think the annotation from your own annotation of whatever you capture in the class is going to be the most valuable part. Yep, yep, yep. So okay, that's a very good question because if you look at this time here, okay, um, a full cycle is from here to here. So if you look at this entire time here, we'll call it delta t, which is the time difference between the two cycles. Actually, technically, it's only up to here, not so much here. Okay, so that would be the period of one full cycle. And when you look at that full cycle, it would have to, it consists of two PDs, right? So if you know the propagational delay, let's say it is 4 nanoseconds, okay, then the full cycle is going to be 8 nanoseconds, which also means now you can determine the frequency because 1 second divided by 8 nanoseconds in this case would be the frequency of this quote-unquote clock. Yep. So the frequency is determined entirely by the propagational delay of the NAND gate in this case, which is then determined by a few factors. The transistor size is one pretty big factor. The second one is actually the length of the wiring. Because the length of the wiring, okay, so let me go back to the picture here. So for those of you who are going to go a little bit more into double E or electrical engineering, in software people always idealize connections, right? All these electrical connections, we just go like, okay, it's 100% simultaneous type of connection. Even CE, computer engineers, will tend to look at physical connections or wiring as perfect conductors, but double E's have to deal with the messiness of physics, okay? Because every wire is not exactly a wire. Every wire consists of a resistor and also an inductor. So that means the signal, if you try to present a really perfect square wave on the input pin, the receiving end of the input pin will receive something that is distorted, that is not exactly a square wave. It will be slightly distorted. Um, so the bottom line is, what were you asking? Yes, yes. So it's not only the propagational delay of the gate themselves, but the wiring. It also influences the frequency of the oscillation. Alrighty. Okay. Yep. Well, because the control of the frequency is only based on the propagational delay, so it's not a very tunable oscillator. So from that perspective, it is not really useful because when you say I need something at exactly 16 megahertz, it would be pretty hard to tune something like this to be exactly 16 megahertz. Now, one thing you can do if you want to really just kind of roughly control the frequency is to, okay, this is definitely a little beyond the discussion of this whole thing here, but you can do it like this in order to introduce additional delay. So what you can do is to introduce two NOT gates here. No, not here, sorry. Uh, there we go. So you can introduce like two NOT gates here and then two NOT gates here. So if you are to do that, the actual polarity of this signal is going to be the same as here because double negation cancel each other out. However, you are now introducing additional propagational delay from the perspective of this node and the rest of the circuit. So that way you are now you're lowering the frequency because you are increasing the period by introducing artificial propagational delay that does not change the actual circuit behavior other than lengthening this delta t. So from that perspective, you have some tunability to the frequency, but it is not something that you can easily fine tune. So as a result, it's a it's a it's a quick and dirty oscillator, but at the same time, you don't have a whole lot of control over the frequency. Yep. Cool. All right. So the next thing we're gonna do is okay, let me see if I can get the page number back. Yep, there we go. So the next thing we will do is to make a truth table. Okay. So after today's lab, you will have one of the two truth tables. I cannot remember which one, but you'll get one of these two. So the truth table is this is S, this is R, those are the input pins, and then we have Q, and NQ is not really useful for the most part, but we're going to track it too. So we know that when they're both zeros, the outputs are both ones. That one is pretty obvious, okay? That one is really obvious. If you change at least one of them to a 1, but leaving the other one to be a 0, and, oops, there we go. Then, in this case, Q remains to be a 1, and Q becomes a 0. Now, what is interesting is if you make S also a 1 after this, then whatever the previous state is will remain. Is that okay? So this is a sequence, okay? You have to start with 0, 0 as both inputs, then you change R from a 0 to a 1, and then you change S from a 0 to a 1, and this will be the resulting state of that particular sequence of input pin changes. Are we good with that concept? Okay? And you can verify this using Logisim. Just build the circuit in Logisim, and kind of do exactly this, and you will see that, oh, okay, so this is how um, this particular sequence works. So the other sequence is going to be similar. In fact, it is really just a mirror image of this one, in a way. So you also start with S and R being zeros initially, and this time you change S from a 0 to a 1, you let R remain to be a 0. What this will do is Q becomes a 0 and Q becomes a 1. Now, we haven't gone through the actual PDNC analysis of either of these sequences, but I'm just telling you that, okay, after the analysis, this is what's going to happen. And then if you change the R pin also from a 0 to a 1, then it will just simply retain the state from before. So these two combined is you can also look at it as a third truth table, SQ, SR, Q, and Q. If both are zeros, then both outputs are guaranteed to be ones. If one is a 0, then and one is a 1, then in this case Q is a 0 and Q is going to be a 1. If it is opposite, then this is going to happen. And in the case of 1, 1, then we use NC and NC to describe Q and NQ. So I have to be very careful. This is a sequence, okay? In other words, things have to occur in this direction. This is also a sequence, okay? The changes of the input pins have to occur in this particular order. This is a truth table, which basically means, anytime you have both inputs being zeros, then the both outputs would be ones. Anytime you have S being a 0, R being a 1, regardless of what it was before, Q would become a 0 and Q becomes a 1, okay? So the first three rows of the actual TT, the truth table, is not very exciting. Okay, what is interesting is the last one. NC in this case does not represent node connectivity. It represents not change or no change. Okay. In other words, when you get both inputs to be ones, it will just quote unquote remember what it used to be. Okay. With the only exception of directly transitioning from 0, 0 to 1, 1 would lead to oscillation. But if you transition from either 0, 1 to 1, 1 or a 1, 0 to 1, 1, it will simply retain whatever state the SR latch was in, and therefore we have the smallest memory device that we can implement using only 8 transistors. So this truth table here is essentially the essence of the SR latch and why it implements the simplest memory device inside a computer. Yep. Yes. Yep. All right. So let's go ahead and kind of go through Logisim because I think if we do it in Logisim, you guys will get a slightly better idea of how this works because different people learn differently. Some people kind of more visual, some people are more experiential, and some people like myself just need to learn all the rules and abstractly kind of figure out the rest. All right, so we're going to create the SR latch. The SR latch is actually part of memory too. So if you go to memory, it has all kinds of memory devices. But we are not going to go for the SR flip-flop in this case. We're going to make our own. So we'll go ahead and go to Project, Add Circuit, SR latch. All right, so we know how to make one. Okay, we need to pull two input pins. Okay, so one is RS, the other one is R. And let's go ahead and label these two accordingly. This is S and this is R. We have two output pins. Okay, so the two output pins would be one we call Q, and then the other one we call NQ. Okay, there we go. This is NQ. And then we have NAND gates. So we go to gates, pull out a NAND, and then change so that the number of inputs is exactly what we need because too many input pins is actually not good. If you leave any input pins not connected, in real life, it is called floating. And any floating pin is going to say, well, it depends on whether you turn on the microwave. If you turn on the microwave, I might turn into a 1. If you turn off the microwave, I may turn into a 0. So, it's not good to leave any input pins unconnected. You always want to make sure that they are stated or they're basically either ground or power. All right. So I'm just repeating or replicating the circuit here. So this part is essentially the same as what I hand drew a little bit earlier. All right. So I don't think I have left enough spacing between, but it's okay. I can get it working. It's just it's not going to look the same as the other circuit, but we can still get it to work. So with this one, I kind of have to go around like this, but it still gets the same thing done. Okay. So what we'll do is we're gonna do something. I mean, right now you get to see, okay, when both inputs are zeros, the outputs are both ones, right? Okay. So we're gonna say, well, what if we change one of them from a 0 to a 1? So we'll go ahead and change, let's say R from a 0 to a 1. Then you go like, oh, okay. So if S is a 0, R is a 1, the output is going to be Q is going to be a 1 and Q is going to be a 0, which is exactly what the truth table is showing you earlier. And then if you go like, okay, what if we change the S pin also from a 0 to a 1? Then it just retains whatever it had before. Okay, so for the purposes of recording, this is what happened. I'm going to take a screenshot just so that I don't forget. Okay, so I'm going to take a screenshot and display that over here and always begin on top. So now I'm going to go back to my circuit and go like, okay, let's change both of them to zeros again. Okay, but I can only change one at a time, okay, because I can only click on one pin at a time. I will show you a way to change both pins from zeros to ones and then see what Logic Sim has to think about that situation, okay? But for now, we are not going to do that yet. So this time, I'm going to go the opposite route, okay? So I think this time we're going to change S from a 0 to a 1 first, like so. And then we change the R from a 0 to a 1. So now you can see how the same two inputs in the earlier sequence, we end up with Q being a 1 and NQ being a 0. But in this new sequence, Q ends up being a 0 and NQ being a 1. So I hope that is now obvious, okay, that this device is quote unquote a very elemental memory device because when both inputs are ones, it simply says, okay, whatever the state is at this point, we'll just keep it. Are we good? All right. So now the question is, so how do we test the case when both are zeros and then we change both pins to ones at the same time? Okay, so I cannot do it fast enough with my clicking. Okay, well, yeah, I don't think I can do it fast enough with my clicking because it doesn't have any way to control the propagational delay of the logic gate. So if it has a feature where it says, okay, this is the setting of the propagational delay of the logic gates and is in numbers of seconds, then I will be able to pull that off. Okay, but since that is not the case, I can't do it that way. But there's an easy way to do it. Okay, the much easier way to do it is to just simply change the circuit, get rid of this wire, and then just go like, yeah, they both come from here. So that would be an easy way to do it. So now I can go back to the poking tool, change both inputs to a 0, and this is like both outputs are 1s, which is what we expected, right? So here comes the moment of truth. As Jack Nicholson, asked, can we handle the truth? I really should have, those little snippets of movies from, kind of really famous lines and then just at my, fingertip so I can just click on one, when it's the right time to do it, right? Okay, so let's go ahead and do it. Change this. If I change this to a 1, it will simultaneously change what used to be the S and what used to be the R both to 1s, emulating the oscillating state of the SR latch. Bam! There we go. What does it say here? Oscillation apparent. In other words, Logisim does detect problems like that, okay? But it doesn't do the same thing that we did earlier, which is, step by step tracing and understanding how the internal state of all of these components are changing when it's going through the oscillation. So Logisim can tell you what happens, but it cannot explain to you why it happens. What we did earlier, okay, let me go back to the table. So what we did earlier, let me see, where is it? Nope. Yep, that one. So what we did earlier in this trace here, that explains why we have an oscillation. Logisim confirms there is an oscillation, but it doesn't explain why there's an oscillation. This explains why there's an oscillation. Okay, so why do we want to know why there's an oscillation? Because if you look up any textbooks, they would just explain to you, yep, this will lead to an oscillation, but they won't necessarily go into the details of, but this is why it is oscillating. So why do I focus on the why of things and not only on the what of things? And honestly, none of you will probably have to work with SR latches after today. So why is this even important? Because it's on the curriculum. No, it is not. If you go to Folsom Lake and take the same class, they won't even touch on logic gates. Okay, they would just start right up with x86 assembly language and programming and whatnot. But why do I get into the why of these things? Yes. You mean your SSDs, your solid state drives? The solid state drives rely on flash memory, and I really do not understand that much about flash memory. What I do know is they have what they call an electron well, so it can store, I guess, a charge, after you program it, and that's how it can retain the information when the whole device is powered off. Yeah, so it's a whole different thing. What we're explaining here does not apply to flash drives. Okay. So the reason why this is important is a mentality. So what kind of thing do you think you need to do as a software engineer that require the same mindset? Exactly. Okay. Just the knowledge of there's a problem with a program is not going to be it's valuable. Okay. So you can at least tell other customers, do not use this feature. It is broken. Okay. So from that perspective, knowing there's a bug and the nature of the bug is actually useful because you're avoiding more customers to be pissed off at your company. Okay. But is it like totally useful? Not entirely, right? Because you really want to fix the bug. So knowing what the bug is versus knowing why you have a bug to begin with so you can fix it are two different things. One leads to the other one, but some people can stop with the first one just to say, okay, I know there's a bug here, but I'm not going to fix it. I do not want to know why there's a bug here. So only the people who look into the why would go like, okay, let me figure out why the program is not behaving the way it's supposed to, so that I can fix it so that it does behave correctly afterwards. So you have to ask yourselves, okay, not only in this class, okay, throughout your education, okay, you have to ask yourselves, do you enjoy debugging? Does it bring you joy or does it bring you grief? Sometimes it's a little bit of both, okay? But you have to ask yourself that question. Because if your answer is, it only brings me grief, I just want to get the program working so I can get a score, so I can graduate, then what happens when your job involves debugging like a lot? Okay. On the other hand, if you get a high just from saying, oh, great, the program is not working. I now have a little bit of investigating to do, and I enjoy the process of investigating, then I would say software engineering or anything that is related to tech is your thing. Okay. No matter how things change, you will adapt because you want to know the why of things. Yep. Exactly. So mistakes or bugs, or generally speaking, things that do not work, they are learning tools. Okay, because until you make that mistake, you did not know that I could have done something like this, and it results in that. Okay, so the only time mistakes are not useful is when people don't look into why it happened in the first place. Okay, if you can make a different mistake every single day and learn from it, you will be a super wise person, in a very short amount of time. Because every single day you're learning something new and you're not repeating the mistakes because you just learned it. It's like, okay, now I understand how this works. Okay, so the next time you do something, okay, let's not do it the same way that I did before. And these are the reasons why I'm not going to do it the same way as before. So I want to point this out because it is a mentality thing, which is not what I'm supposed to teach. There's no way to teach it. I cannot change your mentality. Okay. So for people with a certain set of mentality, I'm not here to change that. Okay. But I am here to point out if you have the right mentality, your work is not going to be as tedious. It's not going to be as challenging. And instead, you go like, oh, okay, this is fun. This is interesting. Even when there's pressure on you. I'm not going to waste your time to talk about, like many years ago when I was still in private sector, what happened. But I can tell you that having the right mentality, every day I went to work, was like going to a theme park to most people, except with the exception of instead of me paying entrance fee to the theme park, somebody paid me to go like, Tech, why don't you get onto this roller coaster ride? Okay. Are you sure you want to pay me that much money to get onto this roller coaster ride? It just doesn't seem right that I'm enjoying myself and you're paying for that. Yep. Alrighty. So let's go to your lab today. All right. So I'm going to set up the lab right now, and I will set it up in a certain way so that people would have enough time to do it. It's called NC and PD. So the way I set this up is a little bit different from usual because, okay, let me explain that as I set this up. Okay. So I will set it up to be today. Today is the 25th. Okay, September 25th. And normally I set up an end time. So with this, I will set up the end time to be anytime today. In other words, there's no, you don't have to get it finished by the end of the lab session because I think some people may take a little bit longer. Um, and then go to build, mm, go to settings. I just want to make sure that we get to see the access code. It is step master, because it's just like the exercise equipment step master. You are taking a step up and then take a step down, take a step up, taking a step down like that, when you're doing the trace. So that's why I use the step master thing. I probably should have used parentheses R because it's a registered trademark, but who cares? There's no IP address filtering, which means you can continue to do this for the rest of today. Okay, so if you cannot finish it today in the lab, you can continue to work on it. And let's see. I'm thinking about whether to do this or not. Yeah, I would leave it on. That's fine. Okay, so return. So that's the quote unquote lab or quiz portion. You also have to submit something at the end of this whole thing, and I will also set that up to be the end of today. So let me go back to, I should probably just kind of collapse these so they don't get in the way. So the other one, let me make it visible so that you guys can actually start on it. So the other one is a Google Sheet submission, which you also have to do. So I'm going to do the same thing here. We just make it due at the end of today, September 25th, 11:59 p.m. September 25th, 11:59 p.m. Like so. All right. Okay. So let me go back to the previous one because there's just one little thing that I should probably point out before you guys, all get started with this one. So let's see. There we go. Make it also visible. Okay, there we go. The reason or the one thing that I do want to point out is how do you make a copy of the Google Sheet document that is in the question? Okay, so that's the only thing I wanted to point out. And it's a little bit tedious because it won't actually let me click on the link because I'm the teacher. So I'm gonna have to go to link options and copy the actual link. So when you click on that link, you don't have to go through all this trouble because you're seeing it as a student. So this is the document. First thing first, you have to first sign in to your own account first. Okay. I don't really care whether it's your personal account or your apps.losreals.edu account. As long as it's a Google account, it will work. So once you sign into your own Google account, go to File, go to Make a Copy, and don't just click make a copy because most people click see a button and they just click the button, especially the one that is highlighted. So don't do that. Instead, go to folder because you want to change the folder to your own Google Drive folder. If you don't do that, it will attempt to create the document in a folder that you do not have right access to, so it won't do it. So make sure that you first sign in to your own Google Drive and then go here to select your own Google Drive. Okay, but since I'm the owner of this drive, it doesn't really matter. But from your perspective, go to all locations, go straight to your own drive and then go to a subfolder if you want to, and then you click select, then say make a copy. Okay, because if you don't do that step and you just go straight to make a copy, it won't work. Are we good so far with that instruction? Okay. Yep. So that's the only thing I wanted to point out. And then the other thing that I want to point out is there are some tricky parts about this spreadsheet. So you guys would go like, I don't see any changes after this point. Yes, I have left some rows intended to be empty. Now, I'm not going to tell you which rows. So when you get to those rows, you will realize, okay, nothing is supposed to happen with these rows. Okay, so I just want to give you a little heads up so that when you get to that point, you go like, okay, yeah, tax said something about that. Okay, it's all good. All right, so with that said, you are free to go ahead and proceed with the lab question. Yeah, let's go ahead and change the scope of the exam so that floating point is not in exam one. So we'll push it to exam two. So the scope will be everything up to but excluding your floating point number discussion. But as to what question will replace that question, I have no idea. A Vulcan can do a mind meld with me and try to extract all the questions and answers out of me at this point, and there'll be nothing to extract because I haven't really thought about it yet. The best way to keep a secret is don't have a secret or shorten the time span of when the secret is actually important. All right. So I think you guys have access to it. Let me write the pass or access code on the whiteboard. You might want to copy that if you choose to continue the work after the lab section. And the reason why I think some people might want to continue to work on it even after the lab section is because it's very tedious. Okay, it is highly likely that someone is going to miss like half a point out of 18, even after a whole hour and 30 minutes. So the more obsessive the people may go like, I'm gonna get those point something something points, and so I want to give those people the opportunity to do so, because they just want to get all the possible points. All right, so I'm gonna go back to my office, get a little sip of water, and then I'll be back. So let me turn off the recorder.